So in this opportunity, I would like to present my current work in my PhD entitled Efficient Graph Learning for Anomaly Detection System. So the outline of this presentation. So first of all, I would like to introduce what is graph anomaly detection is, and then the challenge that to be addressed in my research objective, and then also some research objective, and also that the research task that I would like to conduct in my PhD. So anomaly detection is a system that automate the process to find the rare observation in some data. Since human cannot manually monitor large scale of and fast streaming of data, we need that kind of a system to detect anomaly earlier to prevent some kind of bad effect or detrimental effect. So, so far, machine learning and deep learning can be used to perform anomaly detection, and there are some kind of work over there. They already have some good performance in terms of accuracy to detect the anomaly detection. So the example of anomaly detection so far, such as in the transportation system, probably to check whether there is an anomaly in the transportation system or in the cyber physical system as well. Another example is computer networks and so on. But in this research progress, just focusing on using graph learning for anomaly detection, as graph anomaly detection can bring more advantage to learn the information exchange between entities in the graph data. So there are some example success implementation to use a graph learning for anomaly detection, such as graph deviation network, for example, like in graph learning with transformer to detect the multivariate time series anomalies. And another thing, I'd like to focus on the efficient aspect of graph learning, because most of the state-of-the-art model focus on the improving state-of-the-art in terms of accuracy, but I would like to have a different perspective in improving the efficiency aspect. So here, for example, like how to managing the resource parameters and improving the speed of the training process as well. There are a lot of challenges in terms of accuracy. For example, like model robustness, data imbalance, missing data, and other things. But in this research, I would like to focus on three main challenges. First of all is scarcity relationship in graph data, non-scalable model, and inefficient to learn global dependency. And apart from that, I would like to address it in the future work. So what is the first challenge about scarcity relationship? So basically here, sometimes we found that the data is not in form of graph structure. So there is a undefined graph structure here, or it's come from a non-graph structure data. So there are another challenge here, such as expensive manual labeling or privacy issue. So that's why we cannot draw the relation between data in the graph. So here we hope that we have some kind of a knowledge or some kind of technology to automatically learn the structure of graph data, so that we can take a full advantage to learn graph itself to enhance the performance of anomaly detection. And the second challenge here, non-scalable model. For example, like in anomaly detection, there is a current task, and then in the future there will be another task coming into the environment. How we accommodate that kind of knowledge to the previous model, that's currently is become a challenge. So we need to have some kind of mechanism to consolidate the knowledge, so that we don't want to forget the previous knowledge as well, but we can have an adaptation to the next knowledge to our model. So we can simply say that we can learn from the scratch once the new task coming into our environment, but it's not efficient enough since learning from the scratch for the big data is have a expensive training cost. The third challenge about inefficient to learn global dependency. For example, when in the anomaly detection we have a large scale of graph data, how to perform efficient global dependency, because current GNN model has a problem called overspooting due to repeated local aggregation and exponential computational cost, while we increasing the model depths, so that it is becomes difficult to capture the long range interaction. And from that, we summarize it into the 3 tasks throughout my candidature. The first task is to develop causal graph structure learning, how to build the graph structure among the graph for anomaly detection, and then scalable graph lifelong learning. And the third one is a lightweight graph transformer for anomaly detection to improve the global dependency model. And here, the first task about the causal graph structure learning. So far, I'm working on it on this one, and we have done for the experiment as well, but we'll publish it as soon as possible. So current work, GDN and GTA, they are addressing abnormality in multivariate time series data. So there is a gap here. They are trying to limit number of relation. So number of relation in a graph, and then resulting a very dense graph. So it can be not efficient enough, and lack of model interpretability because it doesn't include the domain knowledge. So here are our proposed methods. First, we divide it into 3 parts here. The first part is about the graph structure learning to pre-calculate the adjacency metric of unknown graph structure. So basically, we implement causal discovery here to calculate the causality between each time series, whether one time series cause another time series, and then we can build a causal graph over there. From that causal graph, we pass that information of graph structure into GNN forecasting to model the normal sample of data, and then in the end, we perform anomaly scoring to check whether in specific time frame there is a anomaly or not. So in this work, we focus on detecting anomaly in multivariate time series data. And on top of that, we are currently arranging for a survey paper for spatio-temporal graph anomaly detection based on this task. And the second task is about scalable graph lifelong learning. We choose a case study in actor-based anomaly detection. The current work, they already propose some method to perform graph lifelong learning, because mostly the continual learning or lifelong learning in machine learning doesn't cover important part in GNN model, such as how to aggregate the information between nodes. So it should be some improvement over there if we want to adjust the previous graph, the lifelong learning method into the graph method. So the gaps, how we use a graph lifelong learning to perform anomaly detection, and how we choose efficient model to consolidate the knowledge while performing lifelong learning. So just like an introduction about what we want to do in the couple's next step. So basically, we want to check whether one actor has performed an abnormal activity or not. So we will check whether there is a new task or it is similar to the previous task. When it is similar to the previous task, we just need to feed forward and then just detect the Anomaly. While it is a new task, we want to consolidate the previous knowledge so that we can update the previous knowledge to have a better knowledge in addressing new tasks. In this second task as well, we already published a survey paper here. So it published in IEEE Computational Intelligence magazine. So it's basically about graph lifelong learning survey. We just summarize the current method of graph lifelong learning over there that relevant to graph neural network. And the third task is about lightweight graph transformer for content-based anomaly detection. It is part of our future works. We, based on my literature review over there, graph transformer can able to improve the efficiency aspect to learn global dependency. So that's why we want to explore more to use this type of methods. So basically, our case studies to use the graph transformer in content-based anomaly detection. How if we want to detect anomaly in specific textual content such as fake news or misinformation, and hope we can find a large-scale graph data over there, and then we can just have some kind of improvement in terms of managing the knowledge in the large-scale graph data. So yeah, that's all my presentation. Thank you very much for your attention.